Welcome you all to this course on defects in material. In the last class, we had a brief introduction to interfaces in material, which is also a type of defect, especially when deformation has to be propagated across, or when we look at optical properties of the material, okay, different properties of the material. The interfaces have a lot of role to play, okay, in how it behaves. For example, if we take a crystalline material, which is perfectly a single crystal, we will find that like silicon, if we take it, okay, if it's a single crystal silicon, we will find that light passes through when it's thin, but when it's a fine grained one, we will find that it becomes translucent or opaque to light. Similarly, when dislocations have to pass through, okay, that is, if a material is a fine-grained material, we always say that it has a better strength at room temperature compared to the ones which are single crystal or essentially a crystal with a large grain size. Not only the grains, but what is the nature of this grain? Okay, what is the nature of this boundary? Not only between the grains, between the second phase particle, all these things have a role to play and decide the strength of the material as far as mechanical properties are concerned. Okay. So having had the brief in the last class, we had looked at the surface energy, okay, and then also what are the different types of classification of interfaces which we have looked at. Okay, when we consider a polycrystalline material, essentially we know that it consists of different types of grains. Okay, grain, that's even in a single phase material, the grain is nothing but a single crystal. Okay, when we say that it's a polycrystalline material, different types of single crystals oriented in different way with an interface between them. Okay, the simplest case what we are considering it here, okay, with some interface, and this is a two-dimensional analog which we are showing it, but the axis which I am showing it is essentially a three-dimensional one. Okay, if you look at the orientation of the axis here and the orientation of the axis here, because since the crystal structure remains that same, the coordinate system is the same, only thing is that it is differently oriented, correct? So suppose we have to represent the grain boundary crystallographically. How will we represent this grain boundary? The way in which we can do it is that from this orientation to reach this orientation, around different axes, we may have to give some rotations, correct? So essentially 3 parameters are required to rotate this axis so that we can reach here. That is how from this grain orientation we can reach this grain orientation. Then the boundary between them is with respect to either this grain or the other grain. Okay, if we take the plane normal, the coordinates of that itself can be, it's like an HKL, it can represent. Okay, but when we wanted to represent with respect to this plane normal, what we require is 2 parameters which are required. Okay, that because any vector, if we consider and represent with respect to this coordinate system, we normally require, we will say the 3 angles have to be given, correct? Like for example, this is x, if this is a vector r, we will find out the angle from gamma these make. But essentially what is going to happen is that, correct, equals 1. That means that only 2 are necessary. The other one is already defined by this relationship. So essentially we require 5 parameters to define a grain boundary. Okay. This is as far as the crystallographic definition of a boundary is concerned. But then comes what is the structure of the boundary, what is the energy of the boundary, all these things. Here we assume that this boundary is a flat boundary, okay, perfectly a two-dimensional surface. But that need not be the case. Quite often the boundary could be curved. That is one. And another is the boundary can have some steps on the boundary. That is one. There could be a lot of defects which are present on the boundary. It's possible that the boundary contains other elements which are also sitting at different sites on the boundary. Second phase particles could form at the boundary. In some cases, one could assume that the boundary itself is an amorphous layer. So if you think of that, the grain boundary as a defect is a very complicated one. Okay. Anyway, let us first consider the simplest case, okay, not the curved ones, but a simple one which is a flat two-dimensional boundary, okay. Okay, essentially what we wanted to look at, what is the structure of the boundary, okay. What are the ways in which we can consider the boundary, okay. One way in which we can look at it is that, as I mentioned just earlier, okay, we can represent it with respect to 5 parameters which are necessary, correct. Using EBSD in an SEM, we can find out the misorientation or the orientation, how with respect to one other grains are oriented. In that process, when we do that, only 3 parameters which are necessary. How from one grain, one orientation in a grain to another grain, how by rotation we reach that orientation, that's what we look at it. So that ultimately gives a misorientation angle, correct? But there in EBSD, we never look at what is the grain boundary structure. We never bother about it. We only look at misorientations. That's how the work is done. That should be very clear. Okay. There are many other techniques, like in TEM, we can look at using diffraction, exactly get some information about the type of grain boundary structure. Okay. So essentially, suppose we take a crystal, okay, a single crystal, and another identical one. We take it with the same orientation it is placed, and if they are joined together, okay, this can give rise to another one single crystal. Like in the case of an ordered alloy, there is nothing like an step which is being created. What I mean by step is that suppose there is a, assume that the planes are there. Here also the planes are going to be exactly that same way. There are 2 ways in which it can happen. This itself can be shifted by some value which is smaller than that interplanar distance. Okay, the planes have to touch each other. That's the way it happens in the case of a single phase. Whereas when it's an ordered phase, they touch each other, but different type of atoms could be there. That is how the antiphase boundary or the translational boundary comes, which we have discussed earlier. Okay. So if that is the case, this is the way they will be touching each other. So it becomes as a one single crystal, joining them together. Suppose we have this sort of a crystal, one crystal, and if I make a small cut like this, making an angle, and join them together, then what will happen is that this is an exaggerated huge. Okay. This is as if from here to here there is a tilt which has taken place. That is what is being shown in this diagram. That is around an axis normal to the plane grain boundary, Okay, that is around an axis which is in the grain boundary plane. Okay, we are now rotating it by an angle. Okay, so this angle could be very small angles. Generally, what happens is that even if we take a single crystal of a material which has been grown by various processes, we will always find that this sort of boundaries do exist. Very small angle boundaries are there. Okay. In this particular case, what we are showing it is essentially is that it's a simple cubic lattice, two-dimensional lattice which we are showing it, and here it's a close packed plane, okay, with lot of ledges which has been created. Okay, each of this ledge, if we join both of them together, this ledge will become like an extra plane, which will be equivalent to introducing an one extra plane, so a dislocation. So if we join them together, now we will have one dislocation and another on top of it, another on top of it, like this will come. And with respect to this plane, okay, this boundary plane, the crystal on either side is symmetrically tilted. Okay, so this is called as a symmetric tilt boundary. Okay, we should understand that essentially one type of dislocation is there, only an edge type of a dislocation kept one on top of the other, and this boundary is generated. What is the other important characteristics whenever we consider as a grain boundary? Another important aspect which we say that if we assume that these boundaries are made with dislocations, okay, generally we know that when dislocations are present, the long range stresses, like if a dislocation is present here, the displacement field will be there all over. Okay, the long range elastic stress is there, large distances. When these sort of boundaries are there, even if they contain dislocations, the long range stresses should not be there within the grain. That means that the dislocation should be oriented in such a way, or the nature of the dislocation should be such that long range stresses are not present. Okay, is it clear? Okay, that is long range elastic stresses should be zero. Then only we can say that is a boundary. Otherwise, it is something like a crystal which has been deformed, correct? Which long range stresses are present. When it defines a grain, that is, we assume that this grain is essentially doesn't contain any deformation. Okay, these dislocations are present at the boundary such that, okay, the rest of the region is stress free. Okay, how can it be done? That's what we are trying to look at it. If you look at the stress field around a single dislocation, okay, I'm just showing the stress sigma z over an edge dislocation. If a single dislocation is there, this is the way the stresses, its isocontours of the stresses are being shown, both tensile as well as the compressive stresses, both are being shown. If we have one dislocation and then another dislocation on top of it, just above one another, then what we'll see that at this bottom there should be a tensile stress. Corresponding to this one, qualitatively, if you look at it, there should be a compressive stress should come. So these stresses will cancel. When this happens on either side, you find that when we have an array of dislocation, finally what we will be left with is long range stresses will not be present. So though we have an array of dislocations are present into the grains, okay, they are stress free. No, it's not. It's essentially a dislocation one on top of the other which it comes. Okay. So from this figure we can understand that it is qualitatively all, that is why it is necessary to have dislocations one on top of the other. That is precisely what it happens when we take a material, okay, and during a recovery process when the polygonization takes place, the dislocations with opposite signs, they cancel each other. Other dislocations come one on top of the other to minimize that energy. Okay. And so far we consider as a symmetric boundary. Now let us look at here. Okay, If we have a dislocation of another, that is, all the dislocations have the same type of a bias vector, okay, the symmetric tilt boundary. If a dislocation with a different type of a bias vector oriented with respect to this, if it is present, okay, again this is a small angle boundary, tilt boundary only, but this is called as an asymmetric tilt boundary, because from this region to this region, if you try to come, okay, with respect to this boundary plane, it is not symmetrically tilted. The tilt angle is here, okay, it's phi plus half theta, here it's phi minus half theta, okay. So essentially these are called as asymmetric tilt boundaries, okay. I will show you some examples where it has been, these type of boundaries have been imaged, okay. So far we looked at just the structure of the simple tilt boundary, okay. And another aspect which we have to look at it here is that angle, the tilt itself is controlled by what is going to be the bias vector, okay, and the separation between the dislocations. That is, angle theta of the tilt will be bias vector by d, okay. That means that if the angle of tilt becomes large, the separation between the dislocations have to decrease. That is, higher the dislocation density in the plane, and only one type of a dislocation is required, okay, then the angle increases, okay. Okay. Then how does the energy of the boundary changes as a function of misfit angle, okay, the tilt angle? This has been calculated by Reed and Shockley in 1950 itself, okay. In a physical review paper it has been published, okay. Essence of it essentially is that this is E0, which is essentially depends upon the material properties. Here it's assumed that it's a material having a modulus mu, okay, an infinite material, and Poisson's ratio nu, okay, and R0 is the core of the dislocation, okay. This is the way the energy is varying, that final formula which we get it, okay. That means that as theta increases, okay, the energy of the boundary also increases. The basic way in which they have done this calculation is assuming that at the end of each of the boundary, okay, like we have some dislocation which is present at a plane which comes from here. There are some dislocations are there, like this from here also. That means that there are two grains oriented differently with dislocations. That means the energy of the grain is high. If they join together, the energy has to add up. What is going to be the energy? That is how this entire calculation has been worked out. That one can look into a details in the paper. Essentially, from this sort of an expression, we can immediately understand that as the misorientation increases, the grain boundary energy gamma increases. But will it go on like this? Go on increasing? It cannot happen. The reason essentially is that this is based on the assumption that each dislocations remain as individual dislocations. Beyond a particular angle theta, we can calculate what is going to be the separation between the dislocations. If the separation between the dislocations become so small that the core of the dislocation starts merging, then the concept of telling that the dislocation is responsible for this boundary itself loses meaning, correct? So this sort of equation is applicable only for a low angle tilt. What is the grain boundary energy which has been seen beyond this value? It is being shown as it's nearly a straight line, okay. But let us see whether it is so or whether it can have some variations, okay. That will become clear. Here what we are showing it is atomic planes, you look at it, close packed plane, how they are arranged. You look at this direction here. And in this one, the close packed direction is in this way. Okay. These two, if you look at it, the misorientation between them is very large, correct? When they come and meet at the boundary, in large angle boundaries, essentially there are a lot of regions, the atomic planes don't exactly match each other at the interface. In the small angle boundary, when the tilt angle is very small, the atomic planes are matching perfectly. Here the atomic plane matching is not there. Okay. There are some cases where what it can happen is that this matching may not be there at the boundary, but if you look at these planes, they appear to be symmetrically disposed with respect to a boundary, correct? Symmetrically tilted with respect to a boundary. That means that if we consider these two, that is the interface where the two orientations, and just continuously change the angle, that is take one grain and another grain, what we are considering it is that the misorientation between them is if we continuously increase. Is it that some orientations there will be a perfect matching which can happen up to an interface? This is what exactly we can say. Here you see that this is one orientation in which these atoms are there. This is another orientation in which it is there. These black dots essentially represent the atoms which are common to both of them. Okay. So now this sort of an orientation, if we try to look at it, here if we try to find out how many atoms are exact orientation in this supercell, okay, compared to the other, we can tell about this is what we call it as the coincident site lattice. Okay. This sort of orientation, this is for a simple cubic lattice which has been considered at an angle 53.1 degrees centigrade, 1 degree. Okay, we can get perfect matching can be. This is like something like a twin orientation. Okay, with a coherent twin boundary comes in between them. Okay. What will be the consequence of it is that when we try to find out the energy of the boundary at some of these angles, that is where this sort of orientation exists, there will be an energy minimization of the boundary will take place. Okay. Here we have only just looked at that interpenetration of it. We do not know what that boundary could be. That is, what we can see is that if we have two crystals, okay, that is grain 1 and grain 2, okay, we can have a grain boundary here or boundary here or boundary there with different types of misorientation between them locally. When we choose them, depending upon the misorientation, the boundary energy can change. What boundary it will choose is the one which generally will have the lowest energy, correct? For various angles of misorientation, we can have cusps like this in the energy. These are also possible. These are all more favored compared to other boundaries with very high energy. Okay. These are all what we consider it as equilibrium calculation. But generally when they grow, they have formed from the melt. There are some restrictions on how they come and join. Okay. Because of that, over a course of time, when we do the aging treatment, we find that initially there will be boundaries with all types of orientations. Gradually during the grain growth, okay, many boundaries will vanish. Finally, it will reach an orientation with boundaries which are having minimum energies possible. That sort of an orientation will be achieved in materials. Okay. So essentially what is important, the important significant fact which one can notice is that there are boundaries with minimum energy configuration. High angle boundaries are there with minimum energy configurations possible. The simplest example is itself is a twin boundary. That in FCC, if we consider 1 on 1 is the closed packed plane, one twins can form. Okay, the coherent twin boundary has got the lowest energy. Okay. Here, what I am showing it is essentially is that when we consider this sort of a coincidence type of a lattice model, okay, this is 1:3, that is sigma equals 3 or sigma equals 5, sigma equals 7 for different axes over which this is the angle by which a rotation should be given, okay, so that the coincident site lattice of this type could be generated. Okay, that's essentially what this shows. Okay, this is one plot which I had, this is one table which I have included, because this table gives the relationship between the grain boundary energy and the surface energy, that is between the solid and the vapor surface. Okay, generally it is seen that this ratio of grain boundary energy to a surface energy turns out to be close to around 0.3. Okay. Okay. So far we have considered a tilt boundary. Okay, the structure of the tilt boundary we have looked at it, because they are essentially made up of dislocations arranged one on top of the other. I am taking a very specific case where a transformation which is taking place in a material, okay, where it goes from hexagonal to a face and hexagonal to a tetragonal system. Okay, that means that there is some change in the C by A ratio. This can happen in FCC also. Okay, because of that, with respect to the matrix, there are two orientations of the crystal is possible. This is exactly like this. Like suppose I take that there is a tetragonal lattice is there. Okay, this is another variant which has nucleated. This is the C-axis. If these two come and join together, since this C by A ratio, assume that it's slightly greater than 1, what will essentially happen is that the interface continuity has to be maintained. When that continuity is being maintained across the interface, essentially the C-axis will be slightly tilted, not exactly 90 degree, some angle that angle will be nothing but the misorientation. That means from here to here, there is a slight misorientation has been introduced. That is what essentially has happened in this crystal structure. Okay, this gives rise to a symmetric tilt boundary. Okay, the dislocations of the boundary has been imaged using a weak beam technique. Okay, we have found out that all the dislocations have the same type of a bias vector, which is one characteristic which the tilt boundary will have. Okay, and the line direction is also almost that same. Okay, then we could find out the boundary plane, and from which we could determine what is the tilt angle, and this tilt angle corresponds to, okay, what is expected from the C by A ratio. Okay, and this is in the same alloy system at some other region. It's not only one type of dislocation. Now you can see that there is another type of a dislocation is also being present, right? Oriented in a different way. This gives rise to, you can see that there is a tilt there. This boundary is essentially an asymmetric boundary. Okay, by doing an analysis, we could find out what is the asymmetric angle. All these details have been there. Okay, so essentially, what we have looked at is that from low angle to high angle, just by varying the tilt itself, we have looked at the boundary, correct? Tilt boundary. When the boundary angle is very small, essentially by dislocations we could try to model the boundary. In other cases, like using at some angle of tilt, okay, essentially there is a perfect matching of the lattice planes occur, which are the like coincident site lattice model. That could be for those type of boundaries, essentially the energy is going to be very small. Okay. This is one type of a boundary. What is another type of a boundary which we can have instead of a tilt? We can have a twist. Like for example, what has been done here is that this is one cube and this is an identical cube. But with respect to one to the other, it is just given a rotation by a small angle. Okay. This is essentially what you can see, that the planes, okay, the lattice planes are there. If you just try to give a twist, okay. But what is essentially important is that here the twist is very small. This is something which is similar to if I take a grid and put another grid on top of it. Okay. Generally, we will be getting a Moire fringe pattern, correct? Essentially, the Moire fringe pattern will have a, which will correspond to similar to the dislocation network. That is essentially what is being shown here. The fringe pattern, if you try to look at it, okay. If some dislocations are generated at this region, perfect matching could be there in the region in between, okay. And by having these dislocations, we could stabilize this boundary, but still maintaining the small twist. Okay. Generally, these dislocations are essentially a screw type of a dislocation which always gives rise to a twist. Okay. Important difference between a twist boundary and a tilt boundary is that in the tilt boundary, one type of a dislocation is sufficient to stabilize the boundary, whereas here one type of a dislocation is not sufficient. There should be another perpendicular type of a dislocation which is necessary. That is for two reasons. One, the long range elastic stresses has to be reduced, that's one. And the other one also is that when you give a twist, it is like a torque. You should have an opposite force somewhere else to stop it. That is what the second dislocation essentially is doing, that part of it. So generally these dislocations will be perpendicular to each other. Okay. These are some of the pictures which has been taken in an electron microscope, where you can see that these are dislocation networks in BCCIN, okay, where hexagonal network of dislocations are there. This is in gamma titanium aluminum, where we had observed this is between one variant and another variant. Okay, both of them, the C axis are perpendicular to each other, and the small c by a ratio is not equal to 1. Okay, slight mismatch is there. Because of that, at the interface, we have a twist boundary is created here. Okay, essentially you can see here also one type of a dislocation and another type of a dislocation could be observed, correct? Yeah. This is another case of a twist boundary. Okay. Here what has happened is that it's the same material, okay, but this side and this side we have the same variant. Okay, I'll not go into a detail how it happens, but finally what is happening is that a slight twist is generated. Okay, a twist boundary is generated. So these two misorientations, okay, using diffraction patterns are essentially using the Kikuchi patterns, which one can see that this Kikuchi pattern is slightly shifted, because otherwise if you look at the normal diffraction pattern, they appear the same. But if you look at the Kikuchi pattern here, this ellipse like one, it is slightly shifted from here to here. Using this, we can try to find, doing it at different orientations, we can find out what is going to be the tilt which is associated with this boundary. Okay. And here also what is essentially important is that in a twist boundary, here you can see that two types of dislocations you could see, one, and on this direction also another type of a dislocation is there. Two dislocations which are almost perpendicular to each other. Okay. Set of dislocations are necessary to stabilize this boundary. This is another example. Here, when you look at the weak beam, you can see that this is one type of a dislocation. Okay, this is another type of a dislocation. Okay, these two together are the ones which is stabilizing this twist boundary. Okay, so far we had considered this twist boundary which is essentially with respect to a small twist angle. But we can have a large, if we go on increasing the twist, then what will happen? The same question which arises like what has for the case of a tilt boundary, the same thing will happen, because that dislocation network has to become smaller and smaller, whether it will be able to accommodate. There are some conditions under which, okay, atom positions, some of the atom positions can perfectly match, okay, and this is like the coincident site lattice, okay, the CSL lattice we can have, okay. Corresponding to these orientations, okay, the boundary energy will be very small, okay, though the twist is very large, okay. That is essentially this high angle boundary could be considered either as a tilt, it could form, okay, increasing the angle of tilt, or we can consider increasing the angle of twist. That's what we are doing. Quite often it can happen that it can have a combination of both could be present. We are considering it as two different cases, okay. So here what is going to happen is that in this particular case also, because this is also a simple cubic lattice which is being considered, okay, this is sigma equals 3 bound, sigma equals 3, that type of a boundary, okay. Here just showing a twin boundary, okay. If you look at this particular type of orientation, the boundary is perfectly coherent, right? And if you look here, this also orientation remains the same, but the boundary plane is a different one, okay. This becomes an incoherent boundary. In fact, in many materials like copper, nickel, many stainless steel, where when we anneal them, quite often one could observe within a grain, sometimes this sort of some small steps could be seen, okay. This is a coherent boundary, this is also a coherent boundary, this is an incoherent one, okay. The energy of the incoherent boundary is very high. Energy of the coherent boundary may be of the order of 10 to 15 millijoule. The incoherent boundary could be of the order of 200, 300. That means that what is the misorientation between these two regions? They remain the same, correct? So, how the boundary will move? Okay, everything is going to be decided by the specific boundary and the particular boundary energy, correct? So many of the kinetics of grain growth and all are going to be controlled by the nature of the boundary and not just the misorientation, okay. That is what is being shown here also, is that the boundary energy, if we plot it as a function of a misorientation, on either side with a small misorientation the energy goes up, and here it's a sharp decrease is there, okay. And in fact one can see also that in a microscope, if you try to see it, generally close to the incoherent boundary, there will be a lot of dislocations could be seen, okay. Whereas the coherent boundary will not contain any dislocations because the lattice matching is perfect across the boundary, okay. This, if you remember about twins, we have discussed in few classes earlier, okay. There we have considered that 1 on 1 plane is a closed pack plane in FCC. That is the plane becomes that's the plane which becomes as the coherent in boundary plane, okay. Okay, let us look at what will happen, okay. So far what we have considered is the different type of boundaries, that is low angle boundary to high angle boundary, correct? What is the and how we can construct, okay, these boundaries. using dislocations, or for the special type of boundaries, okay, where the coincidence site type model could be used. Okay. Then when these type of boundaries form in a polycrystalline material, okay, different boundaries can have different type of energy depending upon what is going to be the orientation between the various grains. That's what is being shown here. That's a grain 1, grain 2 and grain 3. So this is the between grain 1 and grain 3. This is the grain boundary energy. Okay. Between 2 and 3, this is the grain boundary energy. Okay. Gamma 2, 3, here gamma 1, 2. If that is the case, the angle between these boundaries, this is easy to derive. I'm only just giving that formula. That is the gamma 2, 3 divided by the sine theta, 1, 3 divided by the opposite angle. Okay, gamma 1, 2 divided by the opposite angle, which is sine theta 3. These have to be equal. Okay, that is because it's an energy balance which has to be done. If the boundary turns out to be the same type of a boundary, okay, in all along the equilibrium condition, then what will happen is that this angle theta will turn out to be 120 degree. That is where we will have a boundary that equilibrium, all the boundaries have to be of the same type. This angle R will be 120 degrees. Okay. And in fact, we can find out the grain boundary energy, okay, from the grooves which are created when we etch the sample, either the thermal etching, okay, chemical etching, we can do that. Here is one example which is being shown, is that this is the solid vapor boundary which is there on either side, and this boundary, the gamma SV is the energy. This value, we for most of the materials, we have this value which is available. Okay. Then depending upon the angle which it makes with respect to if we draw, okay, this angle theta if we know, then we can calculate, okay, this expression could be derived. Okay, this is essentially that balance of equation which we have written. Okay, 1, 2 and 3 these boundaries, and then we can find out that grain boundary energy depends upon, okay, twice gamma SV into cos theta by 2. This way we can find out the energy of the various types of boundaries could be there. These are all experimental determination of grain boundary energy. Okay. But generally calculations of grain boundary energy computationally, there are lots of difficulties are there, because there is a discontinuity which comes at the boundary. Atoms are not at equilibrium position across the boundary, because the separation between the atoms doesn't correspond to equilibrium separation, but it could be values which are different from that. Calculating what is going to be the energy is an involved process. Okay. In fact, if one looks at the literature, hardly much data is available on computational way of looking at the grain boundary energy and minimization of the grain boundary, and look at what is the type of a grain boundary structure which the material will have. Okay, lot of experimental work is available. Okay, so far what we considered was essentially with respect to a single phase, right? That's small angle boundary and high angle boundary and special boundaries. Okay. These are all the type of boundaries, and depending upon the energy between the various types of boundaries, what is the angle which will make between the boundaries. Okay. Other type of a boundary which we have to consider is essentially is when we have precipitates are there, which has a different composition compared to that of the matrix. Suppose the precipitate and the matrix has got the same crystal structure. Okay. The example which we can take it is copper and cobalt. Okay. Both phases being FCC. Okay. Or achieve many condition many types of precipitation like this can be done where the composition is of the matrix is different, precipitate is different, but the crystal structure is the same. Then in such cases, okay, we'll find that the lattice continuity is being maintained across the interface. If the lattice parameter is also turns out to be perfectly matching, okay, then what's going to happen is that coherency in this particular case will be 0, correct? Because if the lattice parameter is the same, it is perfectly coherent, right? That's one case. But still, the interfacial energy will be there because chemical composition here and the chemical composition is across is going to be different. So interfacial energy will come. This is another case which we are showing where assume this is the matrix. This matrix is inclined in another way, but across the interface, if you look at it, there's a matching is there. Perfect matching is being maintained, correct? Okay. Suppose the lattice parameter is different, okay? In these particular cases, because tomorrow when we talk about the interaction of dislocation, suppose a dislocation is to enter from here to here, what will happen? Because there are some small differences, the modulus will be different. They will have an effect on the behavior of the dislocations, especially on the movement of dislocations, okay? This we will discuss later, tomorrow. In this one, if you consider it, the lattice parameter is essentially slightly different. Here, the lattice parameter is small, and here there is a slight increase is there. But the parameter difference is so small that still it maintains the coherency. That means that how it maintains the coherency? By distorting the planes on either side of it, okay? How much is the distortion which is going to be is determined by the modulus of the material on either side will decide to what extent the distortion is going to be accommodated, whether within the precipitate or within the matrix, correct? And suppose this grows to a very large size, that means that the total strain also increases. At some particular point of strain, when the strain becomes very large, it may not be able to accommodate the total strain. Then it punches out some dislocations, okay, makes the interface incoherent, okay. This can happen in a different way also, okay. If the coherency strain is large also, okay, even at small sizes of the second phase particle, when it punches out a dislocation like this at the interface, okay, these are called as misfit dislocations, okay, they are the Burgess vector which is essentially on the interface plane. Now if you look at it, earlier all the planes were distorted around the interface. Now most of the planes, they maintain a perfect coherency. Only around the dislocation, this distortion is there, correct? So the coherency, the strain could be reduced, okay? These type of interfaces are called as semi-coherent interfaces, okay? And if we know what is going to be the strain, okay, misfit strain, then we can find out what will be that B by D will give, what should be the spacing between the dislocations which is going to come at the interface. That also we can calculate it, okay. So for these boundaries, if we look at it, the this will have a chemical energy also is going to be there, free energy, chemicals plus the strain energy is also going to be there. Both of them together will decide, okay, what is going to be total energy of the interface. And another thing also which one should understand is that, as I mentioned, okay, the smaller the delta, what will happen? the dislocation, the distance between the dislocation becomes very large. If the precipitate size is smaller than this, then what's going to happen? No dislocations will be punched out, and essentially it will be maintaining a coherency. Okay. That's why when the precipitates are very fine, most of the time they are coherent, and if they are coherent, they maintain coherency, they have a spherical shape also associated with it, right? And as the precipitate grows, the morphological change takes place. Okay. Not only that, at some particular sizes, the dislocations will be punched out at the interface, which we call it as the misfit dislocations. Okay, the shape change. This we can calculate also depending upon what is going to be the misfit in the two directions, assuming this interface to be considered as a simple cubic type of a lattice. Okay, one can find out what is going to be the misfit in these two perpendicular directions, which we can determine. Okay, the misfit we can find out, and once we know the misfit, we can find out what should be the separation between the dislocations also. Okay. But these dislocations which are generated, one should understand that they are different from the normal dislocations within the matrix, because the matrix dislocations are glissile, because they can move. These dislocations need not be glissile. Okay, those dislocations are generated just to reduce the strain. Okay. Okay. Suppose interface itself, that is the lattice parameter itself, misfit itself is quite different. Crystal structure could be quite different between these two phases. Composition also could be different. Then the interface could be an incoherent interface. So in an incoherent interface, what happens is that no strain is being accommodated right up to the end of that interface. Okay, the perfect lattice matching is being maintained on either side of the crystal. Whatever is the lattice parameter which is there here, the same thing we'll be seeing right up to the interface. Because whereas in the case of coherency strain, there is a lattice parameter is changing because they wanted to maintain the continuity across the interface, correct? Generally, when the misfit parameter is greater than 0.25, okay, then we say that these are incoherent interfaces. All these types of example, what we can take it is many of the carbides which form in nickel-based alloys, okay, they generally are incoherent, okay, and quite often we can see that the perfect interface could be seen between the matrix and the precipitate. Sometimes to accommodate the strain, what they do it is some dislocations are punched out, because the volume strain there will be a difference between the two phases. To accommodate the volume strain, some dislocations are punched out into the matrix. Okay, this is another type of a complex coherent interface which are seen in many material. Okay, one of the examples which we can take it is, let us take the case of FCC to HCP. The phase transformation, if it takes place, okay, if the lattice parameter remains the same, okay, FCC has got a hexagonal structure and HCP also has got a hexagonal structure. The matching can be perfect across the one-on-one plane, correct? It can maintain the orientation relationship. The other example which we can take it is in iron. It's from BCC. What is the closed packed plane in FCC? It is 1-on-1. The closed packed plane in BCC is 1-1-0. Okay. But if they form with these planes, okay, it's not going to be this is the best plane where the interfacial strains could be reduced to a minimum. Okay, but it's not completely. Because of that, in these sort of interfaces, it is called as a complex coherent interface. Here if you look at the diffraction pattern, okay, there is a slight change in the orientation between the close pack direction in BCC and the close pack direction in FCC, correct? That's what is being shown here. When these two are forming with the 110 plane of BCC parallel to 111 plane of FCC. Okay, this sort of relationship, okay, this small this could be seen in the diffraction pattern itself, okay, from which we can identify, okay, looking at the diffraction pattern taken from this region, we can get information about what is the direction in which the close pack plane in FCC is oriented and what is the direction in which one close pack plane in 111 is oriented, okay. Close pack plane in BCC is oriented, which is 111, okay. This information one could get it. So far what we have considered essentially is that we try to get a simple idea about the grain boundary structure, okay. Consider a single phase material. What are the types of boundaries which we can have, okay, both small angle as well as the high angle boundary. What is the type of structure which these boundaries can have, both for the small angle boundary as well as the high angle boundary, okay, and what are that special type of boundaries, okay, like coincident site lattices which we considered it, okay, and we looked at that special type of boundary which forms in FCC and many other structures like twin boundaries also we considered it, which is a special type of a boundary, okay. That is as far as single phase is concerned. If precipitation takes place, okay, the precipitates could be either fully coherent or incoherent or semi-coherent, okay. If it is fully coherent, okay, the perfect matching across the boundary is there. Only way we can identify them, then the boundary will be very sharp, okay, when it is fully coherent. These boundaries in electron microscopy, transmission electron microscopy, if we look at it, when it is perfectly coherent, there will be a sharp interface will be seen between the matrix and the precipitate. If it is semi-coherent or highly coherent, okay, then what's going to happen is that coherency means that the planes are distorted. That means some straining has taken place around the interface. Whenever straining is taking place, that will appear as a contrast variation, which will be gradually changing, okay. That means that we will, in a coherent precipitate, we will not be able to identify the interface sharply. In such cases, to identify the precipitate, to get the precipitate size, we have to use dark field technique to image the precipitate separately, okay. There are many things like the nature of this mismatch between various types of along various directions in the precipitate. They also do control the morphology of the precipitates. Those aspects we have not gone into the detail. That becomes part of the phase transformation work. Essentially here, what is essentially necessary to define the various types of interfaces, okay. So we have only, that is grain boundaries, small angle boundary, tilt boundary, twist boundary, coherent boundaries we have considered, special boundaries which we have considered, interfaces which we have looked at it in some few simple examples which we have considered, okay. This is all which I wanted to tell about interfaces, but actually this whole interface, if it has to be covered, both the energetics and all aspects of it, we are trying to give a very oversimplified picture of the boundaries, okay. Right at the beginning I mentioned that it's the boundary itself could be a curved one. There could be some precipitate should be there. A lot of complexities associated with the boundaries. At this point, I had just deliberately omitted. Okay, those who are interested can look into various books which I had given some of the references that will give some information about it. Okay, we'll stop here now.